Hello students, myself Syed Hussain, Assistant Professor from Triple Department from KJD College of Engineering and Technology. So as we have seen in the last session, voltage control techniques, and here we have seen that different kind of voltage techniques, right, regarding to the voltage fluctuations. So let me recap the topics what we have discussed in the last session. So here basically in the power systems there will be a voltage fluctuations limited. So that will be considered as a plus or minus 6%. As we have discussed in the last topic, so we need to maintain the voltage constant profile, right? But here, as per government norms, we need to maintain fluctuations levels up to plus or minus 6%. Okay, so that may be a voltage rise, or that may be a voltage drop. These two will be limits up to plus or minus 6%. Okay, now this will be considered as a tolerance. In our power system, the voltage fluctuation limited, that will be considered as a tolerance of plus or minus 6%. Okay, so basically because of voltage fluctuations, we will get the two kind of drops, right? We will get the two kind of things. So what are those here? Either it may be a voltage under over condition, and another will be that under voltage condition. Okay, because of voltage fluctuations we will get these two kind of things, right? So because of over voltage, the voltage rise will be happen, right? And the effect that will be due to Faraday effect or leading load condition, and in case of under voltage, most of the cases because of lagging power factor loads, right? So the over voltage will be occurred due to the Faraday effect, or it may be that leading load conditions, and the under voltage effect will be occurred due to the lagging power factor load condition. Okay, and we have seen the different kind of voltage control techniques. So those are internal voltage control technique and external control techniques and reactive power control techniques, and we have seen that with the help of inductor and capacitor also we can control the voltage levels. So this is how we have discussed in the last session, right? So in external voltage control technique we have seen that some kind of series and shunt compensation techniques, right? So today we are going to see that shunt compensation. So basically in shunt compensation we have to connect one capacitor in parallel with the power system. Okay, so this shunt compensation technique that will be useful for to neutralize the under voltage condition, that is belongs to this voltage drop effect. Okay, whenever voltage drops to its rated value, we have to go to this kind of technique, that is a shunt compensation technique. So in this case I am going to consider two cases. Okay, so first thing is without capacitor. So just consider this is a transmission line, and this will be the sending end side, and this will be the receiving end side, right? So now this will be the transmission line. So as usual it having some reactance value, so that is represented by Jx, and in addition with this we have to take power value, active plus reactive power, PS plus JQS, and in addition with this we have to keep one load in the receiving end, that is a lagging power factor load, lagging PF loads, and similarly it having some active and reactive power, right? PR plus JQR. Okay, so this is the general representation of the transmission system without a capacitor. So here I am not doing any compensation, guys. Not going to do this any compensation in this system. and I am considering one more system, that is with capacitor with compensation. So this is a system which having the shunt compensation technique, right? As usual it having the sending end voltage, and as usual it is also having the receiving end, and this is the transmission line, and this is the load, lagging power factor load, lagging load. And as usual like this, it is also having the active power and reactive power. So you have to represent with this PS plus JQS, and this is also having PR plus JQR. And this is the case for with capacitor. So I need to keep one capacitor in parallel with the load, and always this capacitor connect between the line to ground. Why? Because in the parallel connection only the capacitor will deliver the reactive power to the loads. Here our main aim is to neutralize the voltage level. We need to maintain the constant voltage. Okay, our main aim of the power system is to provide the continuity power supply to the consumers without any interruption. That is our main aim, and we need to deliver the constant power. The voltage should not be fluctuate itself. Okay, we need to maintain the constant. So that one of the best method, that is a shunt compensation technique. So I need to keep the one capacitor here, so which is having JXC. Is it clear? Now here these two diagrams represents, one is for without capacitor, another one is with compensation. With compensation, right? So in diagrammatical representation it is very clear that this is a without capacitor and this is a with capacitor. Now we have to write some equation which is related with the receiving end and sending end. We have a one relation, right? So that is Vs minus X Qs by Vs. This equation represents the relation between the sending end and receiving end voltage level in the transmission line. Okay, but from this diagram, it is very clearly we can understood that reactive power at sending end, that is equal to the reactive power at the load condition. Okay, so that what will happen here? What will happen if you substitute the value here? VR is equals to Vs minus X QL by Vs. So this is the equation which represents for the transmission line without compensation of the system. So let me write here, one equation related with the with compensation. So but if you observe here, the reactive power from the source plus compensation, that equal to the load condition, Okay, so why? Because the active power cannot be delivered by any capacitor, any source. We need that combination of the active power and reactive power, right? So if you look at this, the capacitor which delivers the reactive power to the load, and from the source also I am getting reactive power. So the both reactive powers will be added up and it will reaches to the lagging power load condition. So now let me write the equation. So VR is equals to Vs minus X Qs by Vs. This is the equation which we have from the transmission system. Okay. Now from the equation A, we can write Qs is equals to QL minus QSH. Okay. If you substitute this equation, the source reactive power in equation number 1, what you will get here? VR is equals to Vs minus X into QL minus QSH by Vs. Now I am going to take one condition. That without compensation the receiving end voltage is to be VR1. With compensation I am going to consider the receiving end voltage VR2. Just comparison purpose, just consider that values VR1, VR2. Now if you see here, VR2 is equals to Vs minus X QL by Vs, okay, plus X QS by Vs, okay. So I am writing here once again, I am writing the same equation here, please go through this. VR2 is equals to Vs minus X QL by Vs plus X QSH by Vs. Okay. So if you look at this, equation, just consider this is the equation B. Okay. From equation number B, the VR2 can be written as, VR2 is equals to VR1 plus X QSH by Vs. Right? If you see here, this is the equation without a capacitor, and this equation represents with capacitor, that means with compensation. So what you can observe from these two equations? Simply the VR2 is greater than VR1. Okay, by observing equation number B and equation number C, okay, by observing equation number B and C, we can conclude that the receiving end voltage with compensation is more than, okay, the receiving end voltage without compensation. It is very clearly understood that the voltage profile has been increases. So let me ask you one question, guys. Always we are saying that voltage control techniques, voltage compensation. Why not we are calling current control techniques? Why we are not focusing on current controlling techniques? Why always we are focusing on voltage controlling techniques? Please give me an answer. Yes, exactly, guys. Exactly. So the voltage which is available from the source, but the current, where it is available? Can anyone guess? So the current which is can be calculated or can be considered with respect to the load condition only. For example, if there is no loads, there are no industries, there are no municipal lights, just consider there are no load. So is there any current will pass through the machine? Is there any possibility to pass the current? It is not possible. When you connect the load, at that time only the current will be comes into picture. Until and unless the current will not be comes into picture. So we always focus on the voltage controlling techniques only. Okay, I think it is very clear, right? So with compensation without compensation, here we have proven that the receiving end voltage with compensation is more the receiving end voltage without compensation, right? So, and not only the voltage drop will be rise, one more advantage is there, compensation technique. That advantage is power factor improvement. Power factor improvement. How it is possible? How it is possible? That may be a big question for you, right? So, here I am going to draw one phasor diagram here. So, if you clear about this phasor diagram, then you will be accept that the capacitor will improve the power factor of the system. So, just consider this is the receiving end voltage. Now, just consider this is the load current which having the reactive power component. So, that I am considering that load current IL. So, this phasor diagram represents without compensation of the transmission line. Okay. Now by keeping the capacitor, the capacitor charging current will flow throughout the circuit. So, what will happen here? The current will start from the load side. So, the load current will be comes into picture up to this point. So, this is the IL2 and this will be the IL1. Now, you can observe here, initially the power factor angle cos pi 1 is large here, right? Cos pi 1, and now when capacitor has kept in parallel with the load, the power factor angle has been decreases. So, from this we can conclude that power factor also has been increases. So, we have two kind of advantages with the shunt compensation techniques. Okay. Now, first advantage is the voltage profile has been increases, and the second advantage is the total power factor has been increases of the transmission system. Okay. So, are you clear with this? So, let me ask you one question. So, what will happen if the reactive power is 0? What will happen if the reactive power is 0 in the power system? What will happen if the reactive power is 0 in the power system? Yes? Yeah. So, what will happen if the reactive power is 0 in the power system? If the reactive power is 0, then active power also becomes 0. If the active power is become 0, the total apparent power will become 0. Okay. In the power transmission system, there will be no possibility of the power if the reactive power is 0. Why? What will happen? If you see, most of the students will confuse here. The apparent power will be equal to P plus jQ. So, one of the student will ask like this, sir, if the reactive power is 0, that means Q is 0. So, S is equal to P. So, active power is presented. So, in the power system, the active power is going to flow, right? But you are saying the total power is 0. Exactly, man. So, whenever the reactive power is 0, general representation of the power will be considered as a sinusoidal waveform. But when the reactive power 0, the average value of the positive half cycle, average value of the negative half cycle will become 0. Okay. So, that means you will not get any waveform here. Just like that. So, there is no power. If the reactive power will become 0. So, we need active power and reactive power to get an apparent power in the transmission system. Okay guys, so I hope the topic is understood by you. So yeah, thank you guys, thank you everyone.